YouTube's side right now, and we are ready to go. Alright, so what we're doing today is to continue to talking about the lotto game, and in that process we're going to explain a few terms that has to do with counting. So counting is not quite as simple as what we understand as counting, like 1, 2, 3, 4. We're counting the number of ways of something. Okay, so I'll explain that. So there are a few terms that we need to first understand. The first one is called a trial. Okay, so the term trial in this case is very specific. It refers to a single attempt to do something. I know that is awfully vague. So an example of that is throwing a coin so that you can see whether it ends up on head or tail. Or you can basically draw an object out of a container. Okay, that is also considered a trial. Or you can throw a dart at a dartboard, okay, and see where it lands. That is also a trial. So a trial is basically an individual attempt to do something. In other words, it cannot be broken up into more steps where there are possibilities. So that's what a trial is. An experiment is a series of trials. So the key word here is it is a series of trials, not a set of trials. So when we refer to a series, it means ordering is implicitly important. Some trials, and the choices of a later trial can be influenced by an earlier trial. For instance, if you have 5 marbles in a bag, and you say, I'm going to take marbles marbles out of the bag one by one, and let's just say that you label the marbles 1, 2, 3, 4, 5. Okay, so when you have chosen, if the first pick is number 2, and you don't put number 2 back into the bag, then the next trial can only have 1, 3, 4, or 5 because 2 is already taken out. Okay. On the other hand, there are some trials where it does not influence the choices of later trials, like flipping a coin or throwing a dice. Okay, just because on the first throw your dice has a number 2 on top doesn't mean the second trial cannot also have a 2 on top. Okay, so now we have explained the term what a trial is, what an experiment is, and then the outcome set of. Okay, so now we also have another term which is outcome. A trial has a set of possible outcomes. So in this case, if we're looking at flipping a coin, it has 2 possible outcomes. One outcome is it would land on the head, and then the second outcome is it would land on the tail. If we are thinking about a trial as throwing a dice, then it has, well, a regular dice, a 6-faced dice. Then it has 6 possible outcomes, 1, 2, 3, 4, 5 dots on it. So do we have any questions about what a trial is and what are the outcomes of a single trial? Okay, I'm not seeing any questions in the text channel, so we're going to move on and continue. So now when we talk about an experiment, it also has its own outcomes. But the outcome is a little bit more complex. If you throw a dice twice, for instance, as an experiment, then you have 36 possible outcomes because there are 6 possible outcomes for the first throw, and then depending on the result or the outcome of the first throw, you combine that with the outcome of the second throw so that you end up with 36 unique outcomes when we are talking about the entire experiment of throwing a dice twice. And the outcome of an experiment is usually represented by omega, which is not to be confused with omega in other contexts. So at this point, the only context where we use uppercase omega is in propositional calculus, where omega represents the set of all the connectives, or basically operators. But later in this class, we'll see omega again in the context of time complexity. So there are only so many Greek letters and there are only so many English letters. So we basically have to recycle those. In different contexts, they would mean different things. All right. So, do we have any questions? Does everybody understand the concepts up to this point? I'm gonna let you guys think about it a little bit. Okay. So I'm not seeing any questions. All right. So if there are no questions, I'm gonna move on. So section 3 talks about general counting. So general counting means we only want to count the number of possible outcomes of an experiment. Okay, that sounds pretty simple, right? I mean, it really is simple in certain cases, and it gets a little bit more complicated in other cases. And why do we want to count the possible number of possible outcomes? Well, that kind of relates back to what we talked about the other day on Monday. Because on Monday we talked about the lotto game, right? So we talked about the Powerball lotto game. So in order to play this game, even knowing the jackpot, prize money, you still want to know the odds before you play it. Okay, so and that number turns out to be available on their website too. So let me go back. Oh, okay, I went back a little bit too far. So we go to draw games, go to Powerball, and when you scroll down, it has game odds. Okay, so when you look at game odds, the odds of winning the jackpot is 292 million ish to 1. And when you look at the prize money, okay, when you look at the last draw detail, the prize money is only $169 million. So that means, well, chances are against you if you want to win the jackpot. Now, you can also argue that, but I can win the lesser prizes. Look at this one over here. Okay, it's $1,000,000 and $779,951. Well, but then you also have to look at the chances of winning this particular prize. Okay, you go to game odds, and you basically, if you want to match all of the lucky numbers and not the Powerball, the odds are 11 million or close to 12 million to 1, but the prize money is only 1 point something million, close to 2 million. So once again, it's against you, okay? Because the chances of winning this prize is not that means it's not worth it to buy a lotto ticket. All right. So this is why we're interested in quote unquote counting, because we want to know, what are our chances? Okay, what are the odds of blah 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 happening? All right. So are there any questions at this point about why we are doing this and what counting is referring to? Counting is referring to how many possible outcomes we are talking about that meets our criteria. Any questions? Okay, the class is awfully quiet today with no questions. And I'm looking. Oh, okay, there we go. Okay, still up and running. So another way, even though you guys don't have any questions, I'm going to illustrate graphically one way to look at outcomes, okay? Because outcomes of an experiment. Because I think this is a graphical way to show it, and it might help some people who are more visual learners than concept learners. Because there are different ways to learn, and some people learn kind of more graphically. So when you think about throwing a dice, okay, well, maybe not, maybe just flip a coin, because throwing a dice has 6 branches at each level, and that's a lot of extra work to write. So let's think about throwing a coin, and we want to see whether it lands on the head or the tail. And this is an experiment of 3 coin tosses, okay? So the first toss has 2 possible outcomes. Okay, so we have, okay, maybe we'll just represent it a little bit differently, so we can end up with a head or a tail. So this is what I call trial 0. We count from 0, okay? And then the second trial, now we have 4. We have 4 possible total outcomes. This is trial 1. So trial 1, can also be a head or a tail, but depending on what the outcome was in trial 0, the actual outcome of the experiment up to this point, we have 4 of those. Okay, so now we want to look at trial 2, which is the third trial, so to speak. So once again, it can be head, tail, head, tail, head, tail, head, tail. So now we have 8. So if someone was to ask me, what does omega look like in this case? So if I look at omega, which is the set of all the outcomes of the experiment, yeah, it is a binary tree. Okay, this one really is a binary tree. But when we're looking at the leaf level, and we want to know, what is the outcome of the entire experiment, we have 8 elements in this case. So we got head, 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 tail, head, tail, head, blah blah blah, all the way to tail, tail, tail. Yes, I did skip a whole bunch, but there are 8 of those. All right. So that is what omega is representing. It is representing the possible outcomes of an entire experiment. What about the lotto game, right? So if you want to think about the lotto game, it's going to be a huge tree, so I'm not going to draw the entire thing. But I can certainly draw a part of it. So the first ball that we are drawing, okay, so this is ball 0 coming out of the basket. You can go from 1 to all the way up to, if I remember correctly, 59. Is that kind of the rule? They can choose from 1 to 59. But now the question is, what about ball number 1? It gets a little bit complicated because if ball 0 is a 1, then ball number 1 can only be 2 all the way up to 59. 1 cannot reappear because once you take a ball out of a basket, you don't put it back in the game of lotto. So it does get a little bit complicated depending on what kind of event or what kind of trial we are talking about. Okay, whether we put something back in so it is available again or not. So this is just a graphical way for us to look at the same thing. And now we continue with the note, which is over here. There we go. So if I use this notation where T0 is representing the outcome set of trial I, so excuse me, when T subscript I represents the outcome set of trial I, and it is 0 oriented, then the outcome set of an experiment of M trial would seem to be like this, okay? Because it's just T0, which is representing all the outcomes of trial 0, Cartesian product with T1, which is the trial set, the outcome set of trial 1, and so on. Okay, so that seems to be pretty simple. Well, this is applicable only when T1, is fixed, and T2 is fixed, regardless of how we choose it, regardless of the actual outcome, from the first 2 trials and so on. So if that requirement is met, then the cardinality that we are dealing with is really just a product of all of these things. It's an actual arithmetic product of the cardinality of each one of the T set. Is that making any sense so far? So let's use an example. Okay, so we'll go back to the tablet and we'll look at the example that we just looked at a little bit earlier. And this is 42, so we want page 41. There we go. Okay, so in this case, T0 is just head or tail. T1 is also just head or tail. T2 is also just head or tail, right? So if we want to look at omega, omega is basically T0, Cartesian product with T1, Cartesian product with T2. And a lot of times we don't really want to know omega. We just want to know the cardinality of omega. So when we look at the cardinality of omega, okay, it is the cardinality of T1 times the cardinality of T1, excuse me, the cardinality of T0 actually multiply, this is multiply the cardinality of T1 multiplied by the cardinality of T2, and that is why we use the pi notation. The pi notation, the sigma notation is for summing, because sigma starts with S, which is also the same letter, the first letter of sum, and then pi represents a series of multiplication because it has the same first letter as product. So that's why we use pi, to represent a series of multiplications. So in this case, we have I going from 0 to 2, and then the cardinality of T subscript I, and that's kind of what we are talking about in the notes. Are we still good? Okay, so looks like we don't have any questions at this point, so I'm just gonna move on. In some cases, the set of outcomes are the same for all trials, meaning that T0 and T1 all the way up to they're all the same. So that way, we can actually simplify quite a bit. If we use variable n to represent the cardinality of T, then we can simplify the cardinality of the entire experiment of m trials to n to the power of m, which is exactly what we have in the case of flipping a coin, because in this case n, which is the cardinality of head and tail, because T0, T1, and T2, they are all the same, and m is 3 in this case because we have 3 trials. So the cardinality of omega is just n to the power of m, which is 2 to the power of 3, and that is 8. So I'm just using this as an example to illustrate the concepts. And I'm just checking to see if there are any questions, and there are no questions at this point. All right, so now we got the easy one out. The next one is going to be the complicated one. The complicated one is called without replacement. So instead of just kind of reading the notes, let's go ahead and think of a concrete example. And I'm going to use the tablet for that purpose. And then we go to the last page, and we'll think about a bag. Okay, so here's a bag. It has got 3 marbles. The first marble is labeled A, another marble is labeled B, and then another marble is labeled C. Each trial is basically taking one marble out of the bag, but we don't put anything back into the bag. Okay, so after a trial, we just leave the bag as is, without putting the marble that we have taken out back into the bag. Okay, so that's kind of the rule of this game. So when you look at the outcomes of the experiment, it gets a little bit complicated, because with T0, trial 0, I shouldn't even use the term T0 here. Okay, so we'll just say trial 0. Okay, so the first trial has 3 possibilities. I could have chosen A, I could have chosen B, or I could have chosen C from the first trial. Now when we look at trial 1, it gets a little bit complicated, because if A is already taken out of the bag from trial 0, then trial 1 can only have 2 possible choices, which is B and C. If in the first trial, or trial 0, we took B out, then the second trial, or trial 1, can only have 2 choices, which is A and C. If we took C out in trial 0, then trial 1 only has A and B left as possibilities. Okay, so now let's look at trial 2, which is the third trial. So trial 2, well, it's pretty easy, right? Because after A and B are taken out of the bag, we don't have a choice. C has to be the only one left. And in this case, B has to be the only one left. C over here, A over here, B over here, and then A over here. So that's a little bit more complicated, right? Because we can no longer say that T0 is constant for T0 is still constant. T0 is representing the possibilities or the possible outcomes for the first trial. That would still be common. But when you look at trial 1 and you ask, so what are the possible outcomes of trial 1? Well, it depends, right? It depends on what we took out of the bag in trial 0. So we can't even talk about T1 as if it is just a single set, because there are multiple possibilities. So in this case, omega is basically the tuples. They're all 3 tuples. So we'll have A, B, C. We'll have A, C, B, B, A, C. So I'm not going to write the comma anymore because it just takes extra time, but there are implicit commas between the letters. And then we have B, C, A, and then we have C, A, B, and then we have C, B, A. So that would be our omega in this case. Okay, this is the omega of having 3 trials when the first trial has the choices of A, B, or C. So are we still doing okay with this explanation? This is called with trials without replacement. Once we take something out, we do not put it back in, so that choice is no longer available to later trials. Any questions? Okay. So I'm not seeing any questions in the text channel. Okay, everything is good. Alright, so now we move on. And now we want to know, how do we calculate the cardinality of omega in this case? Well, if you just want to calculate the cardinality of omega, it's not too bad, okay? Because every single trial has one fewer outcome compared to the previous one, right? So that's not too bad. So basically what we end up with here is just in terms of the cardinality of omega, it looks like this. It is basically a series of multiplication starting with I being 0. So n minus 0 is just n, so we start with n. And then we increment I for each iteration of this pi. So we go from n to n minus 1 to n minus 2, and we stop when I equals to m minus 1. M is still representing the number of trials. So when you work out the math, it ends up as n factorial divided by n minus m factorial, and that is also known as permutation. So this is the number of permutation of choosing m items out of a original number of n items. All right. Okay, so let's take a closer look at the derivation. I know some of you are thinking, no, not more math stuff. Yes, math is good. So we'll take a closer look at the math stuff here and see how it works, okay? So when the first step, okay, going from the left-hand side to the right-hand side, we can see that, you're doing something that's pretty stupid, okay? Because all you're doing is to take whatever is on the left-hand side and times 1 to it. Because, if you look at this portion, if you look at the fraction, it has the same expression for the numerator as well as the denominator. So this whole side is just 1. But it is also a little bit interesting from the perspective of when you look at the index, where I start and where I ends, the expression itself is still n minus 1, and is also n minus 1 over here. But when you look at how I changes, it is a little different. This I goes from m to n minus 1. This I goes from 0 to m minus 1. So that allows me to combine the standalone pi to the numerator pi, because when you think about it, okay, this I goes from 0 to m minus 1, and then this I over here starts with m, and it goes to n minus 1. So it basically just continues the series of multiplication from the standalone term. So in the end, I end up with a bigger pi. And the bigger pi starts from 0 and it ends at n minus 1. But this term, so going from here to here is really just working with the index and changing the expression. So instead of using n minus 1 as a term that we are multiplying, I'm doing something that's different. In other words, I am performing some algebra tricks here. So in order to turn n minus I into just I, it is then. So first of all, I have to subtract n from it, and then invert the sign. So basically, when you think about it, if I start I from 0, which means the first term that I'm multiplying is n, and when I reaches n minus 1, then n minus in parentheses n minus 1 is just 1. So basically it becomes n times n minus 1 times n minus 2 all the way down to 1. So if I reorder the thing and start counting from 1 up to n, and we are just multiplying I itself, I get the same thing back. So that is why, okay, so that is why we can do this conversion. Yes, m has to be less than n, because otherwise it doesn't make sense. When you have more trials than you have number of marbles in a bag, that doesn't make a whole lot of sense. So yes, that has to be assumed. And the inequality is probably stated somewhere. Okay. I cannot remember whether it's stated or not. And okay, I'm just checking to see. I guess I never really made it explicit that m has to be less than or equal to n. Okay, they can be the same. M just cannot be greater than n. So Angel is almost entirely right, because he said m is less than n, but m has to be less than or equal to n. They can be the same. But good point, very good point there. Okay, so this expression is just n factorial. Now down here, we also do the same trick. So if you think about it, when I becomes n minus 1, n minus, and then in parentheses n minus 1 is just 1. I mean, that means the last number we are multiplying in this pi is just 1. What about the first one? The first one is n minus m, right? So that means at the bottom here, we just end up with n minus m factorial, because I can basically change the way I index and also change the expression that I'm multiplying for each step of the pi, and we end up with just n minus m factorial. Nope, there's no division by 0. There's no division by 0, because I'm not dividing by 0, I'm dividing by 0 factorial. And 0 factorial is by definition 1. Yep. I know it is misleading, because we are used to looking at, oh, there's a division by 0, but then we forgot that it is not 0 that we are dividing. It is we're not dividing. It's not divided by 0. It's divided by 0 factorial, which is 1. So that is kind of cool. All right. So P is P and M, either you write it this way or you write it this way, or in the spreadsheet it is known as permut, P-U-M-U-T. Okay, that's the name of a spreadsheet function to do permutations. So it's a pretty useful thing, because it shows us the number of permutations when we are choosing M items out of N items. All right. So do we have any questions up to this point? No questions? All right. Well, let's go ahead and play with these numbers. Okay. So let's go ahead and use a spreadsheet and play with that. Okay. So I got a spreadsheet here. It's a leftover from my previous class, but that's okay. We'll just create a new tab for this. All right. So let's talk about the lotto game, right? So we are looking at per mud. Okay. There are 59 choices, and of which we want to choose 5. And that turns out to be, whoa, that is a huge number. This is not even taking into consideration the extra number, the Powerball number. This number doesn't match what the website has. What is going on here, right? Because if we take this number and multiply, okay, if we take the number of permutations and then we multiply that by 29, which I think is 29, which is the number of choices. Is it 26 or 29? I cannot remember. Let's go back to the rules and find out. How to play. Okay. All right. So yeah, it's 26 and the other one is 69. Okay. I It's interesting why they choose 69 for the first one. It's interesting. I'll tell you why I find it interesting. Okay, so I need to change my formula because this one is supposed to be 69 choose 5, or the number of permutations of choosing 5 out of 69, and that's a much bigger number. Now we're going to make it bigger because now we take the number of permutations times 26, because don't forget that you also have 26 possible outcomes for the Powerball, which is completely independent to the other 5 here, which we call the lucky numbers. There we go. So we have this kind of gigantic, huge number here, and it doesn't match what the other website is reporting. What is going on here? Well, that's because we are counting permutations. Permutations are order dependent. In other words, ABC is considered a different permutation compared to BCA and so on. Let's go back to the tablet. You can see in this case we have these as tuples, right? So the tuple of ABC is considered different from the tuple of ACB, which is considered different from the tuple of BAC, and so on. What if somebody is to say, well, guess what? In the lotto game, the order of how we got the numbers is not important. In other words, if I choose the numbers 1, 2, 3, 4, 5, it is considered exactly the same as choosing the same numbers, but in a different order, like 5, 4, 3, 2, 1. What if ordering is not important? What do you think? What do you think we need to do about that situation? So let's think about it in small cases first, okay? And then we'll generalize it to a larger case. Angel is typing something. I'm going to wait a little bit. Nope, not difference. No, we are not we are not using differences. So what we'll do is we are making a new example here. So we are going to change this one to choose 2 out of 3. So we still have the same original bag, which has ABC in it. But this time, not mod, okay? Not mod. Not mod, not subtraction. We'll get to it. Okay. So now we say, just in terms of permutation. So we'll start with permutation, and then we'll get to the point where, but tech, these two should be considered the same, and those two should be considered the same, and these items should be considered the same. So we'll get to that point. Yes. Okay, but let me explain why that is the case. Aiden is correct, but I want to explain it because once you look at a simpler case, I hope the concept would sink in a little better. So we still have the same scenario. Okay, out in trial 0, we have 3 possible outcomes, A, B, or C, and then in the second trial, or trial 1, This one has B or C left. This one has A or C left. And this one has B or A left. Okay, let me just make it so that it's ordered in a certain way. Okay, so now we have these, right? So in terms of permutations, okay, permutations, we end up with A, B, and once again, I'm not using the extra comma in this case just because it takes too much time. Okay, BA, BC, and then we have CA, and then we have CB. So when you look at the set of combinations where ordering is important, this is how much we get, okay? And then now we want to say, but tech, we want to make it so that ordering is not important, okay? AB and BA will be considered the same, AC and CA will be considered the same, and then BC and CB will be considered the same, okay? All right, so now let's look at an entirely different problem, okay? So I'm going to open a new page. And this time I just say, if I give you two things, how many ways can you arrange those two things? Okay, let me say that question again. I'll give you two things, two distinct items, things. And I want you to find out how many ways we can arrange two things, right? So this time we imagine that we have a bag, we have X and Y in it. So this one is pretty easy, right? I mean, the first thing we can choose would be X or Y, but then if we choose X first, then the second thing has to be Y. If we choose Y first, the first thing has to be X. Right? Yes? Okay, so that tells you that if I have two things and ordering is important, then we end up with two ways of organizing those things. So now we think it in a reverse order. Okay, we go back to the previous slide. Okay, 44. So now we say, okay, so we know AB has a companion of BA. Okay, so AB and BA, AC and CA, BC and CB. So now we kind of pair those things up and we say each pair is considered the same. So that means if we want to look at how many ways we can choose something where ordering is not important, there are exactly three ways, which is 6 divided by 2. Where is that 2 coming from? The 2 is coming from here. All right? So when we look at combination, so when we look at the number of combinations of choosing M out of N items, we basically start with the number of permutations first. Okay, so we say, okay, let's start with the number of permutations. And then we realize that we are counting that there are too many items because a lot of these things, a lot of the permutations should be considered equivalent to each other. But how many permutations are considered equivalent? In other words, how many companions of permutations should be considered the same? Well, each permutation has M items, so there are M factorial items to choose those things. And that is coming straight from the number of permutations of M and M. So now, when you look at these numbers, we have N factorial divided by N minus M factorial. That is just P NM. And then this one is actually kind of the same deal too. We have M factorial divided by M minus M factorial. So what do we have? This cancels out to just a 1, which means it is insignificant. So now we end up with N factorial divided by N minus M factorial times M factorial. So that is what Aidan is referring to. So this thing here, number of combinations, is there are several ways to write it. One way is to use the C notation instead of the P. Okay, so we can use C superscript n subscript m to represent n choose m. Okay, and there's another way to write this, which is n m in a pair of parentheses, and no, there's nothing is supposed to be between n and m in between. This is how we write n choose m. It's just another way to write it. Okay, but in terms of computation, this is how we compute it. All right, so here's my question: how many combinations? Okay, so combination means ordering is not important. Okay, so what is the number of combinations to choose 3 out of 3 items? Plug in the numbers. Okay, plug in the numbers. What is C of 3 3? Which is 3 3 like that, which is 3 factorial divided by 3 minus 3 factorial times 3 factorial. What does that boil down to? What do you think? Exactly. It's just 1. Does it make sense? I want you to choose 3 items out of 3 items, but ordering is not important. Does that make sense that the answer should be just 1? Yep. Very good. Let me ask you another question then. What about choosing nothing out of 3 items? And somebody may say, but that should never happen, right? You have a bag with 3 items, and you're asking me to choose nothing out of those 3 items in a bag, and you're asking me how many ways I can choose nothing out of a bag of 3 items. Well, why don't we just figure it out, right? I mean, just plug in the numbers and figure it out. Okay, and that becomes 3 factorial divided by 3 minus 0 factorial, and 0 factorial over here, and that becomes 3 factorial divided by 3 factorial times 0 factorial, and that boils down to just 1, 2. There's only one way to choose nothing out of n items, whatever n is. All right, so now what I'm going to do is to relate the concept of permutation to tuples, which we have seen already. So let me go back to one slide so that we can see it. Okay. Oh, the other one further back. There we go. All right. So these are tuples, right? And this is a set of permutations. Okay. So we're good here. Okay. Now we move on to the next slide, and we go like, how do we look at the set of combinations? The set of combinations is a set of sets. Okay, so we basically have a set that only has A, B in it because ordering is not important, right? Because in a set, ordering is not important. Oh, but in a combination, ordering is not important either. So the set of combinations is really a set of sets because each combination is by itself a set. And then we have AC, and then we have BC. So are we relating permutations and combinations now? Are we kind of good with these concepts so far? Not seeing any text messages. We're good. All right. So now we basically, this is it. What I have talked about so far is just section 5. So section 5 boils down to C and M, which is also C superscript N subscript M. I did not use that anymore over here because it's just harder to type. This is a whole lot easier to type, so I'm just a little lazy here. But it boils down to the same equation. Okay. So up to this point, okay, all the way up to section 5, we are only interested in counting. Okay. But we are not using a systematic way to generate all the possible combinations or to generate all the possible permutations. So now we are sort of more interested in that. Okay, we want to actually get to the outcomes and not just only count the number of outcomes. So now the question is, why would I want to do that? Why would I want to have a way to generate all the combinations? So let's go back to the example again. Okay, let's go back to the Powerball example again. So in the Powerball example, don't you think it's kind of important to understand, a way to generate all the possible tickets? I know the tickets are sort of random. I'm not really sure what algorithm they use, at the store. Like if you go to a convenience store and you buy a Powerball ticket, I'm not really sure what algorithm they use. Does it even talk to? Well, I guess it has to talk to the mothership, so that the mothership knows a particular ticket of a combination of the lucky numbers or the choices of lucky numbers is printed, so it can actually, so the organization, the lotto organization, can actually anticipate how many people are going to win this prize if they come to collect it, and how many people are winning that prize when they come to collect it. So it's really good for budgeting purposes. But that means, they can also kind of kind of even out the tickets, so that they are not so random anymore. Not really sure what algorithm they use. It's supposed to be completely random, I think, but it may not be. What they actually do may not be entirely random. So I'm not sure. Anyway, so the idea is, sometimes we want to generate all the combinations or all the permutations. Um, Not sure how many of you know about the game called Mastermind. Let's go to Mastermind. Okay, because this is a good example of why we may want to generate permutations and combinations. So go to the Wikipedia page, that's perfectly okay. And then we look at the picture of the Mastermind board game. I think some of you might have played this game before. Probably there are apps already, so you can play this game against the computer, or you can play the game against another person remotely and stuff like that. So the game is about decoding. Well, the Powerball mothership cannot know ahead of time what ticket not to sell, because I think it has to sell the tickets first, and then the winning numbers are chosen after the tickets are sold. So they cannot cheat as easily that way. And I think the event of drawing the numbers, is supposed to be public, so people can actually attend face to face, back before COVID-19. I'm not 100% sure about that. Um, yes, yes, I know it is the government. So anyway, with the mastermind, the mastermind game, the way it is played is a person is going to come up with a combination, not combination, I take it back, a permutation of colors. Okay, so I think there are 6 colors that people can choose from. It depends on the variant of the game, but I think the standard game has 6 colors. And of the 6 colors, they can repeat. Okay, so the hidden permutation of pegs, each one can come from any one of the 6 colors. So this is basically a 4 tuple, where each item in the tuple can be from 6 different colors. And then the other person, not knowing the actual hidden permutation, needs to guess what the combination is. So if you think about it, this is a very, very difficult game, because now you have 6 to the power of 4 of permutations, right? Because this is actual permutation, but we're not using the permutation formula, because it is trials with replacement. If you want to, you can make all 4 dark green. You can make all four red. You can make all four purple. Okay, so because you can repeat the same color over and over again, it is not without it is not without replacement, which is to say it is with replacement, and that's why it is not itself a permutation. It is just 6 to the power of 4. So the other person has to make a guess, okay? And then depending on the how it matches, the person who is hiding the pattern would score a particular guess. If there is something that matches both the color and also the position, it will receive either a black or a red peg as a score, depending on the game, the variant of the game. If so, after we count all of those where the color and also the position are matching, after we have accounted for all of those, of whatever pegs that are remaining, if there are ones that are only matching the color but at the wrong position, then each one of those will receive a white peg. So basically, after each guess, we supply a clue. The person who's hiding the actual pattern will supply a clue of, how that guess is scored. And then the idea is to finish the whole thing within a fixed number of steps. I think even if you choose, okay, I have to phrase this carefully. Even without optimizing, okay, but without optimizing, but without a redundant choice, I think it's guaranteed to finish in 8 moves. This article actually talks about how many times it takes to finish it, but if you optimize, it is also guaranteed that you can finish in 5 moves. Okay, so if you want to be the person, if you want a human to be hiding the pattern and have the computer to do the guess, then you need a way to generate all of those permutations. Now, in this case, the generation of the permutations is really quite easy because you're literally just having a, 4 nested levels of loops, and then each one to go through every single color for every single position, and then you compare to the previous guesses and the scores from the previous guesses, and whatever is left, not ruled out, would be the next guess. Okay, that is not optimized. And to make it optimized, you kind of have to understand game theory a little bit. When I talk about game theory, that term, it is not what most people understand about game theory, which is certain theory in game programming. When I talk about game theory, it is actually more of a mathematical concept. So because then you can do what we call alpha beta pruning, blah blah blah. So there are a lot of techniques to optimize the number of times that you need to guess in order to get to the actual combination here. Now, this game is interesting in another way because it's basically, at the end of the day, it boils down to a code guessing, right? Basically you're trying to decrypt, some kind of code by eliminating other possibilities. That particular technique is really useful, has been around for a long, long time. So I'm going to throw in more links here. So the first one is Alan Turing. Okay, Alan Turing. And of course, in real life, he doesn't quite look like the actor who played Alan Turing in the Imitation Game. And I also heard the personality of Alan Turing in the movie does not really match the actual personality based on historical documents of the actual Alan Turing. So anyway, his contribution at the end of World War II was to invent, I think it's called a bomb machine. Its job is to decode encrypted messages using the messages encrypted by the Enigma machine. Okay, so that the British and the Allies can basically decipher German communication actually faster than the Germans can. Which is kind of funny because if you think about it, okay, so let's say German A sent an encrypted message using an Enigma machine to German B, okay, and German B would basically receive the encrypted message in a printed form, right? And then key in those letters one by one on a Enigma machine in order to decode the message. So the whole process is really quite manual, and sometimes people make mistakes. And if you make one single mistake in the process, the rest of the message won't show up. So then you have to ask the other side to resend the message, or you have to rekey in the entire thing. Sometimes the British, using the bomb machine, can decode the message faster and more accurately than the Germans, because the Germans were using manual process, and then the British were using a machine to do it. I mean, they did have to enter those the letters from the original encrypted message manually, but after that it's all the machine's doing, right? And it does do it by the process of elimination. So the technique, that this kind of silly game, okay, is using, is really used in actual applications. Now, for those of you who, I know this is a really old standard, but it's worth mentioning. Okay, in terms of Wi-Fi, there is a old standard called WEP. So when you look up WEP, it stands for Wired Equivalent Privacy, and it can do up to 128-bit encryption. Okay, and the reason why most of you have not heard of this is because you're young. So you missed out the early days of Wi-Fi, where WEP is considered the encryption scheme, in terms of Wi-Fi communication. These days, we do not use web anymore, okay? Because WEP or web is not considered secure at all, because by using the process of elimination and also knowing what certain packets should contain and should not contain, with us watching Netflix and Amazon and streaming all kinds of stuff and whatnot, most web encrypted routers can be broken within a day, just based on the amount of traffic. We are using WPA now. We are using WPA2, and WPA2 also has a variety of ciphers. So, depending on the cipher that is being used, the strength of the encryption can also vary. Yep, but the bottom line, okay, how this is related to what we are talking about, is still the generation of permutations and combinations. In other words, sometimes we are not only interested in counting or knowing the cardinality of omega, we want to know what is actually in omega. Okay, so let me take a look at the time. We got 20 minutes, so I think we can get started with one of these. All right. So let's start with permutation first. Okay, so the notation is, I wouldn't say a killer in this case, but the notation is kind of one thing that we need to get clear first before we kind of get into the mechanism. So the first thing is the notation of trials. So T of I is trial I, and I starts from 0. So that means if we have m trials in an experiment, I should range from 0 to m minus 1. So that's basically what the first paragraph is talking about. Then the second concept or notation is we use T to represent the pool of choices originally presented. In other words, T as a set is the set of possible outcomes, but only for trial 0. Okay? In other words, the bag that contains ABC, that is T. Okay, that is uppercase T. And then we use this notation, omega I of T, to represent the outcome set of an experiment that has I trials. And then trial 0 has T as a set of its possible outcomes. So are we good so far with this notation? because the notation is very, very important in this case. All right, so omega 1 of t is just t itself, because if you think about it, this one here basically says it is an experiment of only one trial. So if you have an experiment of only one trial, it is just the trial itself. So if it is only the trial itself, whatever outcome of the trial becomes the outcome of the experiment. Does that make sense? Okay, so we're good. I really should change the note, to use a better base case. I'm gonna use the actually I'll do slightly better. Hold on a second here. I am going to change my note on the fly, and I can show you guys how that is done, because otherwise you guys will be bored, because you'll be seeing nothing and I just keep mumbling to myself. That wouldn't be good. So let's go back to 00305, and I'm changing my note on the fly, and this is about permutation outcome. Okay, so we'll look for those words. There we go. All right. So the base case that I'm going to use is omega 0 of t is the empty set. So now I'm going to, I got a stuck enter key. All right. So now we'll publish module.latex. Oh, misspelled it. There we go. All right, so let me refresh the web page and get back to the section that we were talking about. All right, so this is what I changed over here. Omega 0 of t is an empty set. Okay, what does that mean? What is this 0 doing here? That 0, omega 0, that 0 means, we have 0 trial. So let's think about this, okay? We have 0 trials, and the original choices, or the original possible outcomes, is t. And I'm asking you, so tell me, what are the possible outcomes? Actually, I take it back. Okay, I have to take this back again. Okay, darn it. I hate it when I'm wrong. And not just wrong, I'm conceptually wrong. That bugs me to no end. All right. And the difference is very small, but it is there. Okay, so there you go. All right. All right, so I have just changed it again, and I do apologize for my conceptual mistake. It is not empty, okay? Because if you think about it, it really should not be empty, because the number of permutations of choosing nothing is 1. So we need to have one item, which is an empty tuple. This is a non-empty set. The only element in this particular set is an empty tuple. All right. Yes, hotfix. Hotfix the hotfix. Hotfix squared. And sometimes the hotfix, one hotfix breaks another hotfix. Just ask Microsoft. All right. So the big U notation is a big union, basically. Okay. But we'll handle the base case first. Okay. The base case is basically saying we start off with a set T that are the possible things that we can choose from. But we want to conduct a very special experiment that has 0 trials. What is the outcome of an experiment that has 0 trials? The answer is nothing. But when we say nothing, it is represented by an empty tuple. it is not an empty set itself, because if this is an empty set, it would mean the cardinality is a 0, which doesn't make sense. Why doesn't it make sense? Okay, so let's go back to, oh, darn it, I just missed it, to the tablet, which is now sleeping. Wiki, wiki. All right, so if you think about it, okay, what is P n 0? In other words, we have n items of which we're choosing 0. Then you guys go like, I have no idea. Well, plug in the numbers, okay? So we know P of nm, okay, this is just quoted from earlier, is n factorial divided by n minus m factorial. So Pn0 is going to be n factorial divided by n minus 0 factorial. So that is just n factorial divided by n factorial, which is 1. And that is why it cannot be an empty set, because the cardinality of the set of all the permutations coming from an experiment choosing 0 out of n items is supposed to be 1. It cannot be an empty set. Exactly, nothing is the outcome, and therefore the set has one item, which is nothing itself, which is not represented by an empty set. It is represented by an empty tuple, because we are talking about permutations, and when we are talking about permutations, ordering is important. And obviously, when you have 0 item in a tuple, there's no such thing as ordering, but it is still structurally a tuple. All right. An empty list is still a list. To answer, to respond to Tom's comment, an empty list is still a list. An empty string is still a string. Sure. Hold on a second. There we go. Sure. So I do want everybody to relate what you see here, which is Pn0 equals to 1, to omega 0 of t being a set that only has one item in it, and that item turns out to be an empty list or empty tuple. Okay, we got some text message coming in, so I'm going to wait a little bit before I go move on. Okay. We are looking at the number of ways of doing something, but there's still one way. Okay, not choosing, having nothing in my hand is still an outcome. That even though there's nothing in my hand, which is the empty tuple, it is still an outcome, and therefore it is the one element inside the set, because this is a set of outcomes. It is the set itself is not a outcome, it is a set of outcomes, and then the outcome of having nothing is still an outcome by itself. It is still a submission. So a quiz that has no answer in it is still a submission. So it is still counted as a submission. Cool. All right. So now that we understand this as the base case, and this is also why CISP430 is really kind of important, because by this time CISP430 should have introduced recursive algorithms to traverse trees, to traverse lists, and so on. This is our base case. Okay. Now, since I did mention recursion and CISP430, so whatever comes next has to do with recursion. So this one, okay, darn it. It is supposed to be let's skip this one. I'm gonna have to fix this because this is still based on the base case having a 1 in it. So let's look at the general case of omega I. Okay, so omega I is the outcome set of an experiment of I trials, and T is the initial set of things that we can choose from. So what is that? It is a union. Okay, so the big U is a union. It's a big series of union. Yeah, we're going to be able to do an example. I'm just looking at the time to see whether we can do it today or not. I think we can do at least a little bit of this today. So this is a big union, and the union is basically a loop looking at each element of T, okay, which is coming from here. And what we do so what are we union over, right? What is the set, each set that we are union over? So the set that we are union over is what is inside this pair of parentheses, the outer parentheses. So it is basically looking at E, which is chosen from T, and this is Cartesian product with omega I minus 1, which is the recursive step. Okay, this is looking at a smaller omega, but the choices available to this smaller omega cannot have E anymore because we have chosen E in this case, so E is no longer available to this omega I minus 1, to basically the sub-experiment that has I minus 1 steps. But the number of choices or the choices available to that sub-experiment cannot have E anymore because I have chosen it at this level as my outcome. Okay, so let's finish this. So this particular part here is not really, I mean, it is not wrong, but it doesn't link back to omega 0, so it's just kind of disconnected at this point. It's not really necessary, okay? It's just one of the steps to help you understand the material, but it's not 100% necessary. All we really need is the base case, which is here, and the recursive case, which is here. All right, so we're going to look at an example. I think with 8 minutes we can do it. And this is going to be, I think it's going to be interesting. And if you search the internet for material like this, you may not be able to find it because this is actually my own thing. So, for better or for worse, it is actually just my own thing. I'm copying certain things onto the tablet at this point, so you can't see anything just yet. Okay, omega I of T is the union of element of T, and then we use E as a single set, Cartesian product with omega I minus 1 of T minus E, and that's it. Okay, there we go. So now we can switch over to the tablet. Yeah, when I teach, I use some material that is tech exclusive. The function g in Aleph No is one of those things too, and obviously the inverse function of that is also one of those things. Okay, so this is what we have. So now we want to make a concrete case out of this. Okay, so let's just say that we want omega 2, which means we want to end up with a set of outcomes of an experiment that has 2 trials. Okay, so this is ultimately what we want to do. And then the original set has A, B, C in it. I use this because we have already seen this example illustrated using a tree. Okay, so I'm hoping that this we can draw some parallels between those. Okay, so the first thing we do is we expand this union, big union over here. So I'm going to use a kind of strange notation, a little bit strange of a notation. We say what happens when E equals to A. Let me present it in a slightly different way. So E equals A, E equals B, and E equals C. So basically, this is just enumerating the loop for each iteration. What can E be? So for the first iteration where E equals to A, then we have the set of A by itself, Cartesian product with omega 1 because basically it's 2 minus 1. And then we have t minus e. So t is ABC, and then e is a. So we end up with just BC in this particular set. This is going to be unioned with the next line where e equals to b. So now we have b, Cartesian product with omega 1. This time it is t minus b. Since then we have a and c left. And then we union again, and then this time e equals to c. So we have c here, Cartesian product with omega 1, and over here we have AB as a set. So are we doing okay so far with the first level of expansion? Are we good here? Well, we're expanding the omega 1 now. We are doing it recursively, remember? So this omega 1 of BC is now expanded here. And it is not the base case because the base case requires it has to be omega of 0. So we are not at the base case yet. So now we say E is B, and then Cartesian product with omega 0 of whatever is left. So whatever is left is B is taken, so it's C. It doesn't really matter at this point, but we'll see. So this is C Cartesian product with omega 0, and what is left is B in this case. So are we doing okay so far with this? I'm basically just reapplying the recursive definition to omega 1 of BC. All right. So now we say, oh, okay, but omega 0 of whatever is always the empty tuple. Okay, that's easy. The set of the empty tuple, I should say. So this now becomes B Cartesian product with the set of just the empty tuple unioned with the set of C Cartesian product with the empty tuple again. So now the question is, what is this? What is B Cartesian product with the empty tuple? Technically, okay, so I'm going to answer that question. So technically it is B, and then the second item in the 2 tuple is the empty tuple. That is technically, okay? So what we would do, because there are two ways to interpret what happens when you have Cartesian product where the elements being joined are tuples themselves. So the empty tuple sometimes is simplified so that we end up with just a tuple of B in this case. And then we're going to union that with a tuple of C in this case, which then becomes the set of just the tuple, single tuple of B, single tuple of C, like that. Are we okay so far? And then the other two are kind of the same thing. Okay, so omega 1 of AC becomes just the set of single tuple A and single tuple C. Omega 1 of BC, same deal, is just the set of single tuple B and single tuple C. Oh, we just did that one, didn't we? So it's AB left. Okay, sorry about that. So it's just AB. So we got A, B over here. All right, so now we have all the omega 1s figured out. So it's time to plug in all the omega 1s back into here. So now we So let me erase this because it's not really useful at this point. So we have A Cartesian product with the set of, let's see, this is BC, so we have the single tuple CB and the single tuple C unioned with B Cartesian product with the set of single tuple A single tuple C unioned with C in a set Cartesian product with single tuple A single tuple B, like that. So that's just me substituting all the omega 1s, okay, back into where they were referred to the first time during the expansion, the recursive expansion. So now we do the actual Cartesian product. So this one becomes AB AC. Remember, we collapse nested tuples. So that's why because otherwise it would be A and then B would be in its own pair of parentheses. But since we're collapsing or flattening nested tuples, and that's why we only end up with AB and AC in this case, that is going to be unioned with BA, BC as tuples, and that's going to be unioned with CA and CB as a two tuple. So you can see that in these unions, each set does not have any overlap with the other two. So the union becomes the set of AB, AC. We just basically have all of the items in the final answer, CA and CB. So that completes the whole process, and we're only 2 minutes, beyond after the scheduled end time of the class. Woohoo! If there were overlaps, then the overlap can only appear once after the union, because after all, we have a union operation here. That means we cannot have duplicate items once we merge all of the unions. But they're guaranteed not to happen. The overlap is guaranteed not to happen in this case. So this is an example of how I applied the recursive algorithm here to generate a set of permutations. So when you have time, okay, because we have a 5-day weekend, from Wednesday to Monday. So when you have time, I want you to read everything that we have talked about today and make sure that you understand the concepts. But we'll also get to section 7, which is a method to generate combinations this time. So the method to generate combinations is a little bit, I would say, a little bit uglier, but nonetheless, okay, it is about the same. And I'm going to change U1 to U0 as well, because U0, it does exist. It is, in this case, the set of an empty set, but it's kind of the same idea. Okay, so I'm going to go off and make some changes to this module like right away. But I want you guys to finish reading this entire thing and also make sure that you understand the concepts before the next class. And when you have time, and I think you probably will have time to do this, I also want you to read forward a little bit and read discrete probability and also events. So these two modules should be read by next Monday. And then we'll have the homework assignment, which may or may not be the same as last semester. I probably would kind of change it up a little bit, but you will need to understand the concepts in events and also discrete probability to do the homework. So that's it for today. Any questions before I sign off? Oh, it's okay. I'm not going to take roll today. No fun words from text today. Yep. Have a good day. Have a nice weekend, everybody. All right, I'm gonna sign off now.